Okay, so look, it's a great pleasure to introduce Dave Lindberg. He's famous for many things. He was a long-time director of UCMP, then chair of IB. He's certainly done his share of service for campus. He's famous for the quality of his wine cabinet. But more importantly, his research in sort of dynamics of marine ecosystems, particularly this system, in space and time. And he has really quite unusual breadth of interest across paleo, neontology, species interactions, and how they play out in time as environmental changes. So, David, at long last, welcome to MVZ Lunch.
Thank you, Craig. It is a real pleasure and honor to do an MVZ lunch, and I thank Craig and the MVZ people for basically having me here today. What I want to talk about, again, as Craig mentioned, is sort of bringing together all available data. I think, as everybody in this room knows, we're facing one of the largest environmental perturbations that this planet has seen, at least with us on it. And in doing that, we need to take all the data we can and bring that to bear at the questions at hand in terms of diversity, abundance, ranges, what's going to be happening. The Grinnell project here has basically pioneered looking at fairly long-term data sets, in this case almost 100 years. And what I want to do is extend that today and take that back further into time, into what some people call deep time. Not really that deep. We'll probably be mostly messing around within 12 or 15 million years, which is an important perspective because this is when most of our fauna and flora in California, in the northeastern Pacific, forms and first appears. And I want to talk about kelp forests. And for all of us in this room, whether it be Rory or Craig or myself, you know, we all have kelp forests in sort of, you know, our minds in terms of what they look like, who the major constitutes are, how things are played out. And kelp forests are really this incredible forest in the ocean with large kelps coming up, some of these kelps growing up to 1 meter a day, and really providing the infrastructure for a whole community. And of course, our favorite organisms, abalone, otters, and urchins, if you're looking at kelp forests along the California coast. These components of the kelp forests have incredibly strong ecological interactions, ones that have been studied almost ad nauseum, primarily in Alaska, California, and the sea otter has come out as being one of the real keystone species in terms of determining the distribution of kelps, urchins, abalone, to the point where it has caused major problems with shell fisheries, whether it be lobster or abalone, in terms of having this very voracious predator at sort of the top of this trophic cascade determining outcomes. And one of the things that has come out of these ecological manipulations, as well as natural experiments, has been the importance of the sea otter and the removal of the sea otter, literally bringing about large barrens of urchins that have literally devoured all the green and brown stuff that existed previously in the kelp forest. Now, I'm talking about assembly and disassembly, and I'd like to propose to you that the removal of the otter, whether it be done through the fur trade of the late 17 and much of the 1800s, or whether it be done through oil spills such as the Exxon Valdez, is in fact a disassembly of the kelp forest community and the trophic cascade. When that otter is taken out, we have a disassembly. But what about an assembly? How did that incredible trophic cascade, with its strong linkages and controlling many of the components that are found in the kelp forest, ultimately come about? And we don't think about this too much. Instead, we almost imagine trophic cascades as perpetual motion machines. When that last taxon comes in, whether it be through migration or origination, suddenly now we have a working trophic cascade with strong interactions. And I would like to propose to you that, you know, these aren't, you know, perpetual motion machines. Instead, there has to be an evolutionary history here. There has to be an evolutionary history of the interactions as different components have been added or subtracted from these communities through time. And one way of getting at that assembly is to take that interacting trophic cascade today, make some assumptions about uniformitarianism. Now, those are my paleo credentials, but basically I can, buy into that. We can discuss later whether or not, there's any evidence for or against. But assuming a uniformitarianistic approach, and that the morphologies, the behaviors, the feeding we see here today has existed in the past, we can basically break out that entire community onto a geological timeline and look for the originations of when those taxa first became available to participate in this community. And we have controls in that, we're looking for particular morphologies. For example, if we find lobsters, which large chelipeds that today crack urchins or shells, I think we're on safe ground in assuming they had that same potential, if urchins and whelks were present in the past, to do the same damage. And we can test it a little bit by looking for some damage in the fossil record, as Gary Vermeer has done. But verifying the morphology, verifying sort of how these animals make a living, when that first occurs, and putting that onto a geological timeline to see when they're originating and becoming parts of these systems. And once we sort of have the geological timeline, then there's all sorts of other things we can bring to bear. For example, the phylogeny, the relationships. Where did these taxa come from in terms of other taxa living today or the fossil record? We can also look at the biogeographical occurrences of these taxa as well as their relatives in terms of their distributions. And we can also look at this then in terms of major events in Earth history, the mid-Miocene cooling, the opening of the Bering Straits, or the closing of the Panamic Portal. And so we can look at these phylogenies, we can look at the biogeographical distributions through time, and sort of get an idea, perhaps, of how these communities were assembled. I never really had a chance to do this because it almost becomes, sort of a self-fulfilling prophecy. If I go out and decide what's important in a kelp bed, then I've already sort of pre-selected the components that I'm going to be looking at and trying to understand. So I needed something that was neutral, something that didn't involve me making the decision as to what was important. And I got that opportunity when this workshop came together, spearheaded mainly by Sean Connell down at the University of Adelaide and Mike Graham at Moss Landing. This was the formal title of the group, working group, but it's quickly turned into why is the seashore brown? Which basically, again, refers back, why do we have this kelp all over the world? What is it biologically and historically? And I was sort of brought in at the last minute because, I had some ideas or at least some data to look back through time at when the seashore became brown. What was amazing, and maybe amazing to some of us in this room, was the number of kelp forests that have been very well studied throughout the world. Over 22 kelp forests that have been well studied experimentally, descriptively, where there is actually some sort of data available in terms of who the key players were. And that became really important for what I was trying to do in terms of bringing in when these originated and sort of what the patterns were for each one of these kelp forests. Our group had individuals which could cover 20 of those 22 kelp forests, and for which there was experimental data. We did not have data for the Galapagos or for the Oman kelp forests off the coast of the Arabian Peninsula. But for the rest of these kelp forests, there were people that in this working group that had actually worked on them, had done experimental manipulations, had done observations, had followed natural experiments as well. And from these, and from their work, we're able to provide a listing of the key components. One of the things that sort of surprised me, and again, it shows my bias in being in California, was basically how rare a sea otter is in a kelp forest. This is the current kelp forest areas that were basically laid out by the group that currently have an otter providing much of the trophic structure. And if we go back to fur hunting days, we don't add that many sites. Only 25% of the kelp forests in the world have anything like a sea otter. And yeah, that was kind of a surprise, because we really have this iconic image, those of us in the northeastern Pacific, of the importance of the sea otter, sea urchin, kelp trophic cascade. But what was able to come out of this workshop was basically these 20 regions with an idea of what the major kelps were in each area, what the major herbivores were, and what the major predators were. That were basically providing structure to these kelp forest communities. And so I ended up with a list of probably close to 150 taxa for these 20 different kelp forests. And from that point, it was a question of looking at the number of systems that each of these taxa occurred in, basically finding well worked out phylogenies for these groups, as well as a taxon age. What was the first occurrence? And it turned out to be surprisingly easy, with the exception of 2 algal species, for which we don't have any sort of molecular clock estimates at this point. And as you would imagine, the fossil record for kelp is very poor. There's about 4 occurrences, and there's a new one sitting down in Cindy Lowy's lab as well in this building. So with these data, it became possible then to go back and reconstruct these 20 different kelp forests and sort of look at how different components have come in through time. And again, with my paleo credentials, I really like spindle diagrams. Basically what you're looking at here is 2 pieces of information. First of all is the age of the taxon that is involved in the system, and then you can also sort of on the y-axis see the diversity of each of these kelp forests in terms of their strong players. So the black bars are representing the predators, the gray bars the herbivores, and the white bars the algae in each one of these kelp forests. I've only shown a comparison here between the Pacific and the Atlantic in the northern hemisphere, as well as a southern hemisphere, mostly a transect through Australia and New Zealand. And when you look at this, there's a really strong pattern that initially comes out, and it's mostly seen here in a comparison of, say, the northern hemisphere with the southern hemisphere. For the most part, in the northern hemisphere, in the far north, we have a relatively simple trophic cascade consisting of algae, urchins, and the sea otter. As we come further south, we start picking up some very old predators in both northern British Columbia to northern California, and southern California and Mexico. And these are sort of sitting on top of this trophic cascade of algae, otters, and urchins. But this is things like lobster. These are Dungeness crabs. These are also large starfish, such as Pycnopodia. All of these have southern ancestry and are in much warmer water than these other taxa at the top. It looks like we're seeing something different in the Atlantic, but this is because this is really not a transect, but rather a circle. So you're starting at the top with the British Isles, going to southern Norway, going to Iceland and northern Norway, and then starting back down south again into the Gulf of St. Lawrence, and then the Gulf of Maine and Nova Scotia. And when you realize that this is circular, you basically see the same pattern. As you get to the southern edges of these kelp forests, we're seeing very old predators coming into these systems in the south. And they're sort of sitting on top of this simpler cascade. We go to the southern hemisphere, it's a totally different pattern. In the southern hemisphere, very old herbivores, predators, and a relatively recent algal presence within the southern hemisphere, partly through migration, partly through origination. So a real contrast between these 2 hemispheres in terms of their kelp forests. And just a simple discriminant function analysis to look at the characters that were basically providing the discrimination between these kelp beds. And the variables here are things like the age of the algae, algae diversification, or algae diversity, whether or not the herbivores are older than the algae or the algae are older than the herbivores in the systems. And the major difference tends to be the herbivores being younger than the algae in this northern area, as well as algal diversity, as well as the herbivore diversity, separating that on the x-axis, and on the y-axis primarily being predator diversity and algal age. So this was an interesting finding, that there were very different patterns in the northern hemisphere versus the southern hemisphere with how these communities, and particularly the important members of the cascade, were being put together. We can look at this now with the northern hemisphere data on the left and the southern hemisphere data on the right, and you can see very strong differences between herbivore age between the northern and southern, not statistically significant, however. Same thing with predator age. Algal age is about the same in both hemispheres, and across the bottom on the other side we're looking at the number of taxa, basically the diversity, and for the most part there really is no difference between herbivore density, herbivore diversity, predator diversity, or the algal diversity. And clearly very, very different, perhaps structuring ecological forces are operating between the two hemispheres. You can also look sort of how these things have been added to the system through time. And we have one old herbivore in the Cretaceous of first occurrence, our predators back into the Mesozoic, but it's really in the Paleogene where the predators in these systems are originating and becoming present in nearshore marine communities. In the Neogene, we see the diversification of the algae and a very, very strong response by the herbivore diversification as well. And as we come into the Quaternary, again, a few more herbivores appearing and very few carnivores. Carnivores have actually, in this system, have tapered off since their original occurrences back in the Paleogene. So again, it isn't necessarily sort of an equal march through time for these different groups. Now I want to sort of give you a detailed snapshot of what's going on with the sea urchins in the North Pacific and ultimately their extension into the Atlantic. This is a phylogeny which has been subject to a beast analysis in terms of providing molecular dates. We have 3 tie points here for the fossil record for the urchins. This study of the algae was done separately. These are, again, the error bars around these different algal genera. This was the one tie point that they had for Neurocystis, which is a major kelp structuring component. And this small barnacle here is a specialist that lives, as far as we know, only on the stipes of the giant kelp. And it's sitting exactly where you would hope relative to the kelp radiation. So when we look at this urchin diversification, one of the things that struck me right away was that you look at the alternation between the sister taxa. Here we have a Western Pacific species, Strongylocentrotus franciscanus in both the Western Pacific and the Eastern Pacific, then back to the Western Pacific, then the Eastern Pacific, and then the Western Pacific again. The urchins are literally diverging on either side of the Pacific Basin, and all of this begins just about the time with the last major wave of glaciations in the Northern Hemisphere. So it looks like we're seeing ice coming down and dividing urchin populations on either side of the North Pacific Basin. However, beginning at this point at about 1.6, what we see after the last Western Pacific taxon is a radiation into the North Pacific, the Atlantic, and the Arctic. And these are the cold water polar urchins. These are the urchins which ultimately get into the Atlantic and set up the kelp forest system there. We can put some time marks on this in terms of the opening of the Bering Strait, but I really want to call your attention to the mid-Pliocene warm period, which was a period just prior to the beginning of the glaciation, very well studied in Europe. And what makes it incredibly interesting is it's during this period that we see the first strongylocentrotid urchins showing up in the Atlantic fossil record of the Netherlands, of Belgium. And shortly thereafter, we have anhydra in the Pacific, and then we also have an anhydra in the Atlantic. And this otter is described from 2 molars taken from 2 different localities, is occurring in the, just under the red crag deposits of northern Europe. These are the deposits that were identified by McNeill and Durham years ago of containing the first Pacific taxa showing up into the Atlantic Ocean. These same areas, these same formations directly under the red crag has an occurrence of a molar that was originally described as Anhydra revii. And what's sort of amazing is this fossil has been around since the 1890s. But it wasn't until 1992 that Williamson, looking at that, realized that this was a Pacific anhydra. This was not an anhydrodon, an anhydrotherium. This was anhydra. This is the Pacific otter in the Atlantic at a period just after the Pliocene warm period. And then subsequently to that, we must have had the extinction of that animal. So here again, knowing the first occurrences of these taxa, putting them into a phylogeny which allows you to map on the current thermal tolerances, which seem to actually correlate with what's going on in the physical world at that time, I believe is a very powerful way of looking at these systems and extending deeper into time for making our decisions. So approximately, my scenario would be approximately 3 to 2 million years ago, we had the wholesale movement of the otter, kelp, and urchin community into the Atlantic Ocean. And its establishment there just after or during this mid-Pliocene warming period in northern Europe. Of course, we had a subsequent extinction of the otter in the Atlantic, and so we sort of lost our top predator at some point from the Atlantic community. However, no good niche goes unoccupied long, and that is what took over. The Atlantic cod, a huge fish, which has the same effect as otters do when it's feeding on urchins. It also feeds, unfortunately, on lobster larvae as well, and has many other effects in the community. Of course, lobsters are predators on urchins. And it's rather ironic that the cod would take over this role, because the cod came from the Pacific as well, initially. And when you compare ecologically the Pacific cod, sister taxa, to what's going on in the Atlantic, it's a totally different beast. It has very little effect in structuring any communities. It's relatively small compared to its Atlantic sister taxon, and has nowhere near the importance in community structure that we see from the Atlantic cod, even though they share a common ancestry. Might be a reason to question uniformitarianism at times. The other piece that sort of comes out of this is how these are basically being assembled. And I have Charles Marshall to thank for the terminology here. In a discussion says, well, Charles said, well, you're just taking them off the shelf and dropping them into the community. And that, I guess that makes sense for an Australian to see the world like that, because that only happens in Australia. But what we have in the North Pacific was an in situ assembly from the existing lineages in the North Pacific in building this trophic cascade. And, you know, an ecologist has to love this. First we have the first occurrences of the algae, followed by the urchin radiation, as well as the radiation of the dugongs in the North Pacific, ultimately the last one being the stellar sea cow surviving on the Commodore Islands. And then lastly, almost as an afterthought, the urchin, or excuse me, the otter appearing in the system. So this is an in situ assembly of basically originations within the area, also following the ecological trophic sort of predictions of the cascade. However, when you look at what's going on in Australia and in the southern hemisphere in general, we have very old urchin lineages, very old fish, as well as crustacean lineages. Our last urchin here, excuse me, our last urchin here, and this urchin may or may not have appeared before or after the kelp. But most of the participants in the trophic cascades in the Australian system are in fact things which were there before the kelp and the kelp forest ever showed up. They were things which were co-opted and basically made a living now and having a major structuring role in the kelp forests of Australia, although they were present and doing other things long before the kelps originated and diversified into the southern hemisphere. So when we go back and sort of look at this now, look at this comparison, what we find is that these pure or completely in situ radiations of the cascade are relatively uncommon. We only see that in the northernmost Pacific, where we have the kelps, the herbivores, and lastly, the otter coming into the system. However, they are present further south, but they're overlaid on top by these predators which have been co-opted into the system, that basically originated before and had a role doing something else in the region prior to the evolution of the kelp and the urchins and the otters. So again, they're sort of co-opted in. This is sort of a mixed off-the-shelf as well as in situ radiations. And of course, what we also have found looking at the experimental data is that the trophic interactions here are very, very strong in this pure community assembly. Very, very strong interactions. Otters can control urchins almost regardless of what the urchins do. It's a very, very high-level keystone predator having this effect on the cascade down through the system. What's interesting is when you get into these systems where the otter isn't present, particularly in Mexico and Southern California, with the exception of San Nicolas Island, what you discover is these predators are not as good as the otter is in terms of maintaining urchin populations under control. That same thing is true in the southern hemisphere. Even though we have spiny lobster, we have all these fish that are basically providing predation, the interaction is not as strong. And this leads me to suggest that off-the-shelf interactions never really equal the power of a predator which has evolved in situ with its prey. That's sort of the take-home message from looking at this comparison between the southern and northern hemisphere. And this has been manipulated in New Zealand, it's been manipulated in Australia, and there's some thought that maybe overfishing has sort of changed the dynamics in such a way that the predators really can't get the numerical numbers they need to control the urchins. But some of this work has been done at some of the marine labs in protected areas like Goat Island and North Island, New Zealand. And again, there really isn't, there's a strong effect, but in terms of really having that huge top-down control like the sea otter does, we don't see that in the off-the-shelf assembly systems. So we can look at this in another way in terms of coming back to our cartoons of the origination of the group. And what you'll notice is that these predators are coming in very early on, but here's our little trophic cascade, our in situ assembly, sitting down here, primarily in the Neogene. And we see that same pattern in the Atlantic. We don't see that pattern in Eastern Australia, but we also see it in South Africa. And South Africa is a real outlier because South Africa in the discriminant function analyses, as well as the other values for its predator, groups much more with what we see in the Northern Hemisphere, and particularly in the Atlantic, than what we see in the Southern Hemisphere. So South Africa is sort of an outlier with regards to how that community has basically been put together. As I mentioned, we can also sort of look at the biogeography. Where do these taxa first occur? And all of the taxa highlighted there are tropical to subtropical taxa. They're associated with warm water originations, and most of their clade is still found in subtropical, tropical areas. These are taxa, as you saw from the earlier spindle diagrams, are moving up into the southern range of the kelp forest and becoming predators in the kelp forest community. But they're coming out of warmer water as they move in. So if we think about global warming and what's that going to do to the nearshore environments around the world where we have these kelp forests, how is that going to affect the kelp forest? Well, obviously there's going to, kelp is a cold water, cold temperate taxon, so there will be certainly some effect on the kelp. But one of the other effects is basically bringing older predators from subtropical waters into these temperate regions as these areas as these areas warm up. And so in looking at this and thinking about it, do we have any other examples where a warming has basically actually favored one part of a trophic cascade over another? And actually, it was kind of funny because I went back to work I did almost, 25, 30 years ago. And it's in one of the most unusual places you would think to look for these kind of data. It's actually on Isla de Guadalupe, located about 150 miles off the coast of Baja California. You'll notice that Isla de Guadalupe rises from the ocean bottom. It is not sitting on the continental shelf. This is a shield volcano, which basically sort of pops up into the Pacific. Never had any human occupation in terms of indigenous people, although it was visited by sealers extensively through the 1800s. But what's more amazing about Isla de Guadalupe is along this entire east coast of the island, there's over 15 Pleistocene fossil localities on a volcanic island, which basically provides snapshots of the former communities on Isla de Guadalupe. And they're quite amazing. They basically date to 123 and 114,000 years ago, which places them almost smack dab in the 5E interglacial stage, the last interglacial that we were basically in. The sort of infrastructure of the community is dominated by this coral, hermatypic coral porites, which has extensive branching as well as large coral heads, as well as a beautiful little cowrie about 2 inches long, which also shows up in this deposit. One of the things that makes this amazing is this coral and this cowrie are Hawaiian. And they're sitting as part of the Isla de Guadalupe community 123,000 years ago. But perhaps even more important is if you break down the trophic structure of the nearshore mollusks that are recovered from the fossil record, you have a community that does not exist anywhere in the Pacific today. If you look at the Northern Californian province taxa that are present, almost every one of them is an herbivore. As a matter of fact, 20 herbivores and only 1 Californian carnivore. However, from the Panamanic, which is a subtropical, tropical province to the south, every carnivore in that system, with the exception of 1, is basically out of Mexico, the Gulf of California, or even further south. This includes 5 species of cones, large whelks, large theids. We have a tropical community feeding on a temperate community just 120,000 years ago off the coast of Mexico, and the infrastructure of the community in terms of the coral being provided from Hawaii. Quite a mixture of different communities coming together and forming what we have here. This is a time, the 5e stage, which is about 3 degrees C, warmer than what we are looking at today, even higher than the Holocene climactic optimum. And as you can see in our past interglacial cycles, we've also been up here in terms of temperature. So this temperature spike at 5e seems to be about 2 to 3 degrees higher at the time that fauna was interacting than today on the island. And we tried to get at this by basically plotting the ranges of what we had from the southern community going south and the northern community, southern community going north and the northern community going south, right? Yeah, because this is getting warm, okay. What we were looking for was a thermal band in which all of those taxa could co-occur based on their current thermal tolerances. And once we sort of had it for the molluscan fauna, all 37 taxa in this case, we could bring in the hermatipic coral, which has a very, very narrow range with regards to maintaining its symbiosis, and overlay the hermatipic coral range on that, which tended to be a little bit higher than what we got from the mollusks, and then basically parse the difference for a range between 18 and 23 degrees C at 120,000 years ago. This would roughly be a 2-degree increase, similar to what we saw in the oxygen isotope data for the 5e stage. A 2-degree increase appears to have completely changed the composition of what we think of as being sort of a Baja California community, to include Hawaiian taxa, tropical taxa from the Panamic, all interacting with California taxa, and not Southern California taxa necessarily. The same taxa that are at Moss Beach, Monterey, are the taxa that were at Isla de Guadalupe 120,000 years ago. We did not see the herbivores necessarily, at least we could pick up, that were basically moving northward. It may be happening again as well, and it's kind of surprising. There's several groups studying this right now, but Mexacanthina lugubris, which is a Mexican predatory whelk, is now the dominant predator in the intertidal community below Scripps in La Jolla. And it is moving up the coast, and it's a predator. And again, what we don't understand about these, particularly the neogastropod predators, these are crawlaway larvae. And yet they're the first ones which are showing up as they are apparently moving north because of the warming. Calletii, typically found south of Point Conception 20 years ago, is now established in Monterey Bay. Again, another warm water, very active predator, carnivore, moving up the coast of California. These may be sort of the opening onslaughts, but it's very similar to what we saw as the outcome of Isla de Guadalupe 120,000 years ago, with just a 2-degree increase. So when we sort of reflect back on kelp beds, they sort of look alike. It's the same laminarian algae, which is basically providing the infrastructure, whether it be South Australia or Maine, or the more familiar California or South Africa. But the components in that interaction that are determining the abundance of the kelp, namely the urchins and their predators, are very, very different and have been assembled in very, very different ways. And I think just with this one example, particularly for nearshore marine habitats, we have to think about the history and, again, go deeper than the Grinnell Project, go deeper than our historical records, and actually start using the fossil record. It's not going to work for all taxa, it's not going to work for all habitats. It works especially well in certainly the marine settings, but I think there's some lessons we can take from this and some generalizations as well as what we can make from kelp forests. First of all, not all kelp forests are created equal. Northern and southern hemisphere are very different in how they were assembled and assembled through time. In situ radiations and off-the-shelf assemblages appear to give very different sort of interactions in terms of the strength of the top predator interaction. We only have an N of 1, so we need other communities to look at to see if this is something that we can generalize in terms of predators and prey that evolve together versus ones in which a prey species may come in or a predator species may come in and not have as strong of interaction. And even though we can sort of dichotomize these extreme in situ and off the shelf, the mixed examples are the most common throughout the world, where you do have an in situ radiation, but as you move towards the tropics, you start picking up tropical and subtropical predators primarily that are basically coming in. The only place we saw old warm water herbivores coming in was basically the radiations in the southern hemisphere, namely in Australia and New Zealand. The latitudinal gradient is important in community composition and history. Where you are along the coast in looking at kelp forests is extremely important. And the history of that latitude in terms of past climate change is something that really needs to be factored in and looked at. And Isla de Guadalupe provides a great example of that. Lastly, there's probably not a general panacea for predicting what's going to happen to kelp beds with global warming. Instead, we're going to need regional specific models that are able to basically look at the history and provide estimates and what may happen in terms of an impact as we literally warm up the kelp beds and the nearshore environments. I want to thank my collaborators, Jared Burns, John Erlandson, Jim Estes, Mike Graham, Charles Marshall, and all the participants of the Why the Seashore is Brown workshop. I never would have ever had an opportunity to pull these data together and to look at them if it hadn't been for the expertise that was contained within this workshop. And thank you all for listening today as well.
Someone turn the lights on, please. Push those buttons at random, something will happen. David does have to go to a lecture at 1, but
The field at 1, not the
field,
lecture.
even better. We have a few minutes. So, Tony.
So Dave, I was really interested in the difference in the strength of interaction between the otter examples and all the other ones. I wonder if what's explaining that is just that it's a mammal rather than a fish or
a crustacean.
metabolic
Yeah,
environment.
exactly.
So it's going to have stronger interaction with that.
Yeah,
One
that-
otter will do. the
Yeah,
job.
I think that's another possibility as well, is that, you know, with that mammal and that metabolism and, you know, that animal is just one eating machine. So that may be a big difference. I mean, sort of like, you know, Bob Payne's initial ideas about how starfish could crawl up and take 2 days to eat a mussel and have an effect. I mean, obviously it has an effect, but, you know, put a shorebird on top of that, where you got a vertebrate that's out there and can do, you know, 20 mussels in you know, one low tide. Yeah, I think the phylogeny and the groups are very important as well, Tony. Bill?
With the near complete demise of the Atlantic cod, now what's happening to the urchin population?
The urchin populations initially have, it depends on the area. The Gulf of St. Lawrence is different than Maine, which is different than Iceland. But what is happening, at least in some of these areas, is as soon as you basically knock down the cod, you get greater survivalship in the lobsters, and then the lobsters sort of take over and start munching down on the urchin populations. Again, they can't take them down the same way the otter can, but they certainly have an effect, and they are basically get a release from predation by the overfishing of the cod. Most of the cod, the big cod, were taken out in the 30s and 40s, and so it's just a pittance which is left there now.
Do you have any insight about how the community assembly of the kelp forest in the Chilean coast is? Because I'm thinking it might be different of what happened in Australia and New Zealand, because this dynamic of off the shelf, or like pulling groups from other areas, would be different. Consider that in the Eastern Pacific there is this big coral reef system, which is not present in in the Western Pacific. There's this big coral reef system.
Right, in terms of Isla de Guadalupe having access to the Hawaiian corals, in terms of its reefs?
No, I'm thinking if considering the southern hemisphere kelp forest,
Mhm.
the one in Australia and New Zealand, those are close to big coral reef systems, which
Right.
is not the case of the west coast of
Not
South
so.
America.
Most of these are rocky reef taxa, though, not so much associated with the coral. The only place the corals came in was in Isla de Guadalupe, which was a total surprise. No, most of these are rocky reefs. Yeah.
I realize the timing may not be perfect on this, but it seemed to me that your urchins were coming in before the predators. In the southern hemisphere, yes. Absolutely. The urchins are co-opted out of Central Stephanus and tropical lineages that basically are there. So all we can say is that they are there eating something. Probably fucoids at that point, or red algae or other algae. But ultimately they're going to get co-opted and be feeding on the Macrocystis, the Apollonia, and be in that system. Yeah, that's a bizarre thing about the southern hemisphere, David. I'm sorry I didn't make that clear, is all those things are being co-opted off the shelf. They're pre-existing, and today they're having a role in kelp forest structure in Australia and New Zealand.
David, just sort of thinking about the South African system relative to these others. In the South African system, we don't have such strong top-down predation. You get this very tight link between sort of the lobster and the urchins and the abalone.
Yeah.
And then it goes through cycles. Is that as a consequence of that system being sort of on its own, or do you see those very strong mid-level effects?
No, I think it's being on its own, and of course it's pulling in its lobster from the North Atlantic. It's probably pulling in a lot of the kelps from the North Atlantic as well, and then you have your indigenous sort of radiation of the abalone and another urchin there, which again is unique there. So I think I'm sorry, Roy, but South Africa is just sort of off by itself in this in this particular. You're not doing much better, but.
So one thing I got from that is that the North Pacific system is really atypical.
Yeah,
You probably
absolutely.
don't have this dynamic of this latitudinal
absolutely.
shifting of predators and
Yes, absolutely.
diverse weak predators coming
Yeah.
back and forth.
Yeah, absolutely. I mean, and of course, I mean, it's like Drosophila is a model organism. It's the worst kelp forest system you could pick to basically study. I mean, it's easy to study because you only have 3 things to manipulate, and that's probably been why it's been attractive. But it is such an outlier compared to the rest of the kelp forest, where the dynamics, I think, are much more interesting, and the history is much more interesting and much more complex.
Yes.
What's the origin of the marine otter, the one that is in South America?
That is a typical otter species, Lutra, which is Lutra felina, and it doesn't have the role in particularly down in the fjords and sort of south of Port Lamont that you're seeing with R otter. It's feeding on, and it's weird again because we have the same tegula, the same fissurella, the same lineages that basically are found along this coast in the kelp beds are down there in Chile. But it's a very, very weak interaction. And the Chilean otter will go out and forage and everything else, but most of it's done in fresh water. It just is not having that impact yet. It may be on its way, but it's a separate parallel evolution in terms of marine feeding than what we saw within Hydra back in the Pliocene.
Okay, thank you very much, David. I've been let you get Yeah, that's great.
Thank you.
So is there something community Is that what I'm talking about?
Yeah, oh, right, yeah. Yeah, but I think,
Traje enrollarlo.
I mean, at least in the...
Players also follow the traffic.
Oh, you just want to say that?
Players are trying to interact.
Right, and you're going to have natural phenomena which are going to come in. El Niño's totally changing.
No,
But, the amazing thing about so strong. Wiped out 600 years of California. 20 years later in Chile, it still has.
A little concerned. I'm like,
So
I put
there's
a
very
put a
different
God in
dynamics
about
as well
things.
that need to be factored.
Right.
It's primarily that, and it's different lineages. You know, there was a Lysoniopsis down there, and here was Macrocystis and Urchins. It was fun.
Hey, Tony.
And I just want to say, Russell, thank you.
Yes.
That was awesome. That was really good. Sorry, I just want to say, that was awesome to hear some of this stuff. It's really good. And meshing with a lot of it.
Yeah, I just have to get them transferred over from Hearst right now. But I'm expecting, Jenny's got all the, I needed, but the thing that slowed me up is I really needed to have all the disruptor samples. And Jenny basically put that together. So I'm hoping that they're going to be over probably in the next 2 to 3 weeks.
Okay,
And we'll get going.
all right, yeah, so let us know as soon as they're
Yeah,
here.
absolutely.
Because Natalia's,
I'm waiting.
We're going to put you to work just as fast as we can.
absolutely. All right, see you, Dave, that's
See you
good,
later.
that was interesting.
Thanks, Tony.
I think it's just mammals versus fish, though.
Yeah, no, I think
I mean,
think that's a lot.
rather than an assembly story, I think it's, you know, who the predator is, like you need.
Right, but it still comes in late,
Yeah,
which is
Yeah. Yeah.
which is interesting. But I don't think it's so much it's part of the assembly story. It's part of why we have such weak interactions.
Yeah,
in those
exactly.
other places.
Yeah,
It's basically
yeah.
we're not dealing with this mammal.
right.
Which is nice because then it adds a whole phylogenetic overlay to what's happening as well.
Yeah, no, it's a cool story.
Not just timing.
Very cool story.
Okay.
Is it possible to see like a phylogenetic consequence of the different assembly? Because in which hemisphere the herbivores arrive? Oh, in the south, the herbivores arrive
The herbivores and the predators are there long before. Excuse me. We get any. There we go. We get any showing up of the kelp.
Right.
So when the kelp shows up, it's like they're already around, and you just pick them up and drop them in.
Right. So I was thinking, if you have, like, let's say, herbivores before predators, it's like when you have an island where all the herbivores they radiate and start doing
Yeah.
different things like gigantism. and
Yeah,
stuff.
right. Exactly.
Is it
Exactly.
possible to see something like that?
I don't know if anybody's looked, but yeah, I mean, it might be in the data.
Because if you have
Yeah, no, so compare sizes in terms of what's going on with the different size classes of taxa.
Or